Alright, welcome to another video. Today we're going to be looking at how do we split fractions like this, into partial fractions. And there are three forms that I'm going to cover in this video. And the first one is the example on my screen. If we have a fraction that's in this form, for example 3 over x take 1 times x plus 2, we can rewrite this fraction as two partial fractions added together. So it's a over x take 1 plus b over x plus 2. And if you have a look here, this fraction here is the same as these two fractions here. All I have done is I have split this fraction down the middle, so I have one fraction that's separate here and another fraction that is separate here, like that. So now all we need to work out is what on earth are the values of a and b. To work out the values of a and b, all I'm going to do first is I'm going to merge these two fractions back up on the right-hand side of the equation. I'm going to make them all under one denominator. So the way I'm going to do that, I'm going to look at this first fraction, and I'm going to times both the numerator and the denominator by x plus 2. And for this fraction, I'm going to times both the numerator and the denominator by x take 1. That way we can have two fractions with the exact same denominator. So this I'm going to times by x plus 2. And on the bottom we will have, we just need to times it by x plus 2. And on the bottom we'll have this. And for the other fraction, I'm simply just going to times the numerator and the denominator by x take 1. So here we have it. We have two fractions with the same denominator, and so we can then combine them to get a times x plus 2 plus b times x take 1 divided by x take 1 x plus 2. And on the right-hand side, on the left-hand side, we still have this fraction unchanged. Okay, and what do you notice here? Well, I notice that on this side I have a fraction, and on this side I have a fraction. And I can recognize that the denominators of both these fractions are the same. And if we know that both of these fractions are the exact same, doesn't that mean the numerators must also equal each other? The numerators are the same, denominators are the same, and hence the entire fraction is the same. So that's what I'm going to use now. I'm going to now say that if the numerators are the same, just comparing numerators here, I can say this is equal to all of this. So 3 is simply equal to a times x plus 2 plus b times x take 1. Now what we can do is we can let x equal to some sort of a strategic value. And what I mean by that is we can say this bracket, we want that to equal to 0, and this bracket, we want it to equal to 0. And why would we do that? Well, this is the whole purpose of null factor law. Well, not necessarily, but we just want to cancel one of these variables over here and solve for the other one. We can't solve for both of them at the same time. So I'm just going to let x be some value. In this case, I'm going to say let x equal to 1. And the reason I've done that is this bracket here will simply equal to 0. So if I do this, then 3 is equal to a times 1 plus 2, because I let x equal to 1, plus b times 1 take 1. And you can notice that 1 minus 1 here simply cancels out to 0. So this entire term has been gone. And this side, I have 3 is equal to 3a. And if I solve this, a is simply equal to 3 divided by 3, which means a is equal to 1. That is my solution for a. Now, I can let x be another strategic value. I can let it equal to minus 2. And if I let it equal to minus 2, you can see that I have this. Let x equal to minus 2. Then I have 3 equals to a times minus 2 plus 2 plus b times minus 2 minus 1. We can see that minus 2 plus 2 is equal to 0, and a times 0 is simply 0. So this entire term cancels out. And so what I'm left with is 3 is equal to minus 3b. And minus 3 I got by doing minus 2 minus 1. That's minus 3. And b is simply equal to is equal to 3 divided by minus 3. And simplified, that's equal to minus 1. These are the two values of b which I have got. And that helps us a lot now, because we knew that at the very start we said this equation here. Our original fraction can be split up into two fractions like this, where a is some constant and b is some constant. Well, not anymore, because we already know what a and b are, we just work them out. So I can simply say that this fraction, 3 divided by x take 1, x plus 2, is equal to 1 divided by x take 1 minus 1 divided by x plus 2. And if you're wondering where I got the minus from, it's plus minus 1 on x plus 2. And this simply just simplifies to this here. And that's how the partial fraction example for this question would work. You can have a rewind, but we're going to have another look at a different example now. Similar example to the last one, but how would we solve this? Well, because it looks very similar to the previous example, we can simply say that this fraction can be split up into two separate partial fractions, and we can split them right down the middle. So we could say this is the same as a divided by 2x take 1 plus b divided by x plus 3. And now we're going to do the same steps as before. We're going to rewrite the right-hand side by merging them as one fraction. So what I can do is I can multiply both the top and the bottom of this fraction by x plus 3. And I can times the top and bottom of this fraction by 2x take 1. Okay, because we want them to have the same denominators. So if I continue with this, I'll get a times x plus 3 divided by 2x take 1 times x plus 3. And for this fraction here, I'll get b times 2x plus 1 take 1 divided by 2x take 1 x plus 3. And we can do the same thing as before. We can just merge them together because they have the exact same denominators. And we know that's all equal to the fraction on the left-hand side of the equation, our original question. Okay, so now that we have this here, we can say that because the denominators are equal to each other, we can say the numerators must also be equal to each other. So that means 12 is simply equal to a times x plus 3 plus b times 2x take 1. And now we can do the whole process of letting x equal to some value that we desire. And in this case, I want this bracket to cancel out the a term, and I want this bracket to cancel out the b term. So all I'm going to do is I'm going to let x plus 3 equal 0. That means x equals minus 3. That's my value that I'm going to let equal to x. So continuing on, I get 12 is equal to a times minus 3 plus 3 plus b times 2 times minus 3 take 1. And I can see that 12 is equal to, this term cancels out because minus 3 times, the minus 3 plus 3 is simply equal to 0, so this cancels out. And this term here, I can see that 2 times minus 3 is minus 6. Minus 1 is equal to minus 7. So that means minus 7 times b. And if I solve for b, I can say that b is equal to minus 12 on 7. There we have it. And now the other value I'm going to let equal to 0 is when 2x take 1 equals to 0. And solving for this, I can say 2x equals to 1. That means that x equals to a half. And if I do that, I can say, when I let x equal to a half, I can say 12 equals to a times a half plus 3 plus b times 2 times a half take 1. And we already know that because we let x equal to a half, this entire section of my equation cancels out. So that means 12 is equal to a half plus 3 times a. And a half plus 3 is the same as just a half plus 6 on 2. So that's equal to 7 on 2. So 7 on 2a. And to get rid of the 7 on 2, I can simply times both sides by 2 and then divide by 7. So 24 is equal to 7a. And that means a is equal to 24 divided by 7. So these are my two values of a and b. Much more disgusting than the first example, but nonetheless, still worked it out in the end. So that means our final equation, if we remember at the top here, we said let our partial fraction equal to this. So our final equation for this lot will be a equaling to 24 on 7, and b equaling to minus 12 on 7. So 24 on 7 divided by 2x take 1. I'm going to say plus minus 12 on 7 divided by x plus 3. And for those of you who noticed, same as the last one, we can just say that the plus and the minus are the same as minus. That is how you split this partial fraction. And if you wanted to simplify even more, we can simply carry the divide by 7 to the denominator. So all we can say is, instead of saying 24 on 7 like this, we can say 24 and 7 on the bottom like this. Make it look a little bit more pretty. And on the bottom, we can say the same thing for the right one. 12 here, 7 here. That is your final, most simplified partial fraction. Okay, so those were a few questions of similar style when we're doing partial fractions, but this one here looks noticeably different. And you can see not only is the numerator, not only does that have some sort of a quadratic, in all honesty, the partial fraction, the numerator doesn't really matter what it is. It's always the denominator. If we inspect the denominator for this question, we can see we still have a linear root, we still have a linear factor, but now we have a quadratic factor. And in this case, the first thought that some people might have is to simply factorize this quadratic. So if we factorize this quadratic, we can get 2 more linear factors, and hence we can get 1 more partial fraction. But if you also notice with this, we can see that this quadratic is non-reducible. In other words, we cannot reduce this into real roots. We cannot reduce it into real factors, x take a, x take b. So what do we do then? Well, there is an easy fix. All we have to do is simply modify what our partial fraction looks like. Instead of our partial fraction looking like a over the first fraction plus b over the second fraction, the second factor I should say, what we would have instead is we would still have a over the first linear term, so a divided by the linear term, but instead of b divided by the linear term, we would have bx plus c divided by the quadratic. Okay, and this only applies if this quadratic here is non-reducible. If it was non-reducible. So let's continue on with here. So now that we know what our partial fraction would look like, we can just do the same steps as before. So on the right hand side, I'm just going to merge both these fractions together, and the way I'm going to do that, I'm going to times the top and bottom of this fraction by the quadratic, and then I'm going to times the top and bottom of this fraction by the linear term. So all I'll have now is a divided by x take 2, but now I have to times the top and bottom by the quadratic, so x squared plus x plus 1 divided by x squared plus x plus 1 plus the linear term, so bx plus c, I'll times that by x take 2. Divide by x take 2, x squared plus x plus 1. And now what I can do is I can simply merge these two fractions together. I have a times x squared plus x plus 1 plus bx plus c times x take 2. All over x take 2, x squared plus x plus 1. And I'm going to write it a little bit nicer. Looks like this. Now, what I can do here is I can I can simply say that all of this, all of what I have here, it's a bit disgusting, but all of this is equal to x squared plus 6x plus 5. All divided by x take 2, x squared plus x plus 1. And because the denominators are already the same, I can simply just equate the numerators. So that means that x squared plus 6x plus 5 is equal to a times x squared plus x plus 1 plus b x plus c. Ugh, how disgusting is this? So I can write it as such. Now what I can do is I can simply just substitute in a nice number, and I can already notice that this factor here, I can cancel it out to give me a 0. I can cancel this out, and by doing so, if x take 2 equals to 0, if I let that equal to 0, that means x must equal to 2. So continuing on, I know that x squared, so first of all, let x equal to 2. That means that 2 squared is 4, plus 6 times 2 is 12, plus 5 equals to a times 2 squared is 4, plus 2 plus 1, plus b times 2, so 2b plus c, times 2 take 2. And you can notice that the 2 take 2 is just 0, so 0 times all this just cancels out. And I can just start simplifying. 4 plus 12 is 16, plus 5 is 21, equals to 4 plus 2 plus 1, which is 7a. That means that a is simply equal to 21 divided by 7, which is 3. That is one of my solutions right here. The next thing I can do is I simply need to solve for the values of b and c now. And there are two ways of going about this, but the way I like to do it is simply by matching coefficients. So if I already have the value of a, I'm just going to plug this back in to this equation here. I'm going to rewrite this equation again. So x squared plus 6x plus 5 equals to 3 times the quadratic plus bx plus c times x take 2. All I'm going to do on the right hand side is I'm going to expand everything out. So I have 3x squared plus 3x plus 3 plus I can do my FOIL expanding. So this times this plus this times this, which equals to bx times x, which is bx squared, minus 2bx. And then I can say c times x plus c times minus 2, which is cx take 2c. And I'm just going to factorize this to make it look more like a quadratic. So I'm going to compare and rewrite the coefficients. Particularly, I'm going to combine these two terms. I'm going to combine these terms together. And I'm also going to compare these two constants together. And let me just get rid of the colors. I'll give you a second to highlight these just so you understand which one I'm talking about. So if I were to merge them together, I will have 3 plus b, and factorized out is x squared, plus 3 take 2b plus c, factorized out will just give me x, plus, and then the final constant, 3 take 2c. And on the right hand side, I still have the quadratic. So what you should notice here is I have a quadratic on this side. So what you should notice is I have a quadratic on this side and I have a quadratic on this side. So if you notice the quadratic, the coefficient of the x squared term should equal to the coefficient of the x squared term on this side. The coefficient of 6x should equal to the coefficient of x on this side, and the coefficient of the constant, or the constant in this case, should simply equal to the constant. So what I'm going to do is I'm going to say that the coefficient of the x squared term, 1, is equal to the coefficient of the x squared term on this side, 3 plus b. Solving for this, I get b equals to 1 take 3, or simply minus 2. And if I compare the constant, 5, I can see that 5 is simply equal to 3 take 2c. And solving for this, I get 2c is equal to 3 take 5. That would mean that c is simply equal to minus 2 divided by 2, which is equal to minus 1. And there you have it. Those are my values for a, for b, and for c. So rewriting the whole thing, I can say my original fraction. My original fraction in this case was x squared plus 6x plus 5 divided by x take 2, x squared plus x plus 1. I can say all of that is now equal to this fraction at the very top. I can say it's equal to this here, and I've just worked out the values for a, b, and c. So scrolling back down, I can say that it's equal to 3 over x take 2 plus minus 2x minus 1 divided by x squared plus x plus 1. And those of you who are astute will notice that I can just factorize the negative 1 here to get negative 2x plus 1, and that becomes plus negative, which is just minus. So I can say that's the same as 3 divided by x take 2 plus, minus 2x plus 1 divided by x squared plus x plus 1. And that is how you get the partial fraction for a quadratic, or for a fraction which has a non-reducible quadratic on the denominator. Okay, let's have a look at one last example. In this case, we're going to have a look at a fraction which doesn't have a non-reducible quadratic. In fact, it is fully reduced. It's going to look like this. Okay, we can see that we clearly have 3 linear factors. And what I mean by 3 linear factors is on the denominator, I can see I have x plus 1, x take 1, and another x take 1, hence the x take 1 squared. So I have 3 partial fractions. Okay, so I can generate 3 fractions on the other side of the equation. Except this one here is what's known as a repeated factor. We have a reduced repeated quadratic factor, and hence our partial fraction will look a little bit different. Our quadratic, in this case, will yield us a partial fraction of a divided by x plus 1 plus b divided by x take 1 and plus c divided by this last factor whole squared. This is what our partial fraction will look like for this question. These are the only three that you would need to memorize for the WASTE curriculum anyways, and abroad it'll probably only these three that you would need to really memorize. And you just have to do a bunch of practice before you can start recognizing which form to use. And you can also come back to this video and rewind whenever you want to have a look at which factor you can use. Okay, so carrying on, we know the form of our partial fraction, so I'm just going to do the same steps as before. First step, merge everything on the right hand side to one fraction. So to do that, it's a little bit more tricky, but in this case, I'm just going to times the top and bottom of this fraction by x take 1 whole squared. Because remember, I want everything to have a denominator of this. So if I already have x plus 1 on the denominator of this fraction, all I'm missing is the x take 1 whole squared. So that's exactly what I'm going to do. So a times x take 1 whole squared divided by x plus 1, x take 1 whole squared. So now you can notice the denominator is the same as the denominator in the question. So what do we times the top and bottom of this fraction to get the same denominator as the starting question? Well, I already have an x take 1. I'm missing an x plus 1. And I need another x take 1, so I have x take 1 squared. So on the top and bottom, I'm simply going to times by x plus 1 and x take 1. So now you can see the denominator. All I'll simply get is x plus 1, x take 1 whole squared. And last but not least, the last term, I already have the x take 1 whole squared term. So all I need to do now is times by x plus 1. So it'll be c times x plus 1 divided by x plus 1, and you guessed it, x take 1 whole squared. Now we can merge all these fractions together, and one thing I like to do normally when I do these questions is I like to just skip the whole merging of these fractions. I already know that comparing the numerators and comparing the numerator, they should equal the same thing. So all that means is 2x plus 10 is equal to a times x take 1 whole squared plus b times x plus 1 times x take 1 plus c times x plus 1. So now what values do we let x equal to? Well, I can see here that if I let x equal to 1, I'll let this fraction and this fraction cancel out. So I'm going to do that first. Let x equal to 1. So the equation I'll get is 2 times 1 plus 10 equals to a times 1 minus 1 plus b times 1 plus 1, 1 take 1, plus c times 1 plus 1. And you can see 2 times 1 is 1. 1 take 1 is simply 0. And if 1 take 1 is 0, that means this entire term will multiply to 0 and hence cancel out. The same logic applies here. 1 take 1 is 0, and if I'm timesing by 0, this entire thing must equal to 0. So this also cancels out. So what I'm really left with, what I'm actually left with, is 12 on this side, and I did that by doing 2 times 1, which is 2, plus 10, which is 12, is equal to c times 1 plus 1. And 1 plus 1 is 2, so I know c is simply equal to 2c. So 12 is equal to 2c. Then I can say that c is equal to 12 divided by 2. That means c is simply equal to 6. That's one value right there. The next term I'm going to let equal to a constant is this here. I know that if I want x plus 1 to equal to 0, if I want x plus 1 to equal to 0, that means that x must equal to minus 1. So let x equal to minus 1. And I'll give you a moment to work out what the constant that you arrive at will be. Okay, so if I were to sub in minus 1, I get minus 2 plus 10, which is equal to 8, is equal to a times minus 1 whole squared. And that's the same as minus 2 whole squared. And you know minus 2 squared is 4. So I go a equals to 4a. 8 equals to 4a. Plus, if I substitute minus 1 into this fraction here, I know that minus 1 plus 1 is equal to 0. That means I'm timesing by 0. And that means this entire thing should cancel out here. And the same logic applies to this term here. Minus 1 plus 1 is equal to 0. That means this entire term should cancel out. That means the c is also cancelled out. So this is the only term I have left. And solving for this, I can say that a is equal to 8 on 4, which means that a is simply equal to 2. So I've got two values. Now we're in a little bit of a dilemma. What is the last value of x? What can I let x equal to now, such that I can cancel out some terms and find out what my missing value for b is? Well, we don't have any other numbers. We let x equal to minus 1, we let x equal to 1. We've exhausted all possible options to cancel out brackets. But don't fret, we have a bunch of numbers we can test, and the next easiest one is to let x equal to 0. Let x equal to 0. So if we let x equal to 0, and looking at the very top of this equation here, okay, we can say that 2 times 0, which is just 0, plus 10, so it's just 10, is equal to a times 0 take 1 whole squared. 0 take 1 is minus 1. Minus 1 whole squared is just 1. And a times 1 is just a, obviously. Plus b times 1 plus 1, which is just b times 2. Sorry, not b times 1 plus 1. We're saying b is equal to 0. So x is equal to 0. So that means it's 0 plus 1, which means it's 1, times 0 take 1, which we know is just minus 1, plus c times 0 plus 1, which is just 1. So all I have now is 10 is equal to a plus b times 1 is b times minus 1 is minus b. So we get a times minus b plus c. We already have the values of a and c. So that means 10 is equal to 2 take b plus 6. And solving for this, we can say that 10 is equal to 8 take b, and that would mean that b is equal to 8 take 10, which means b is equal to minus 2. Those are our values for a, for b, and for c. So if I were to go to the very top of our example, copy back what we have here. Okay, we already have the values of a, b, and c. So we know that a is simply equal to 2. B is equal to minus 2. And C is equal to 6. And those of you that remember, plus minus, you guessed it, is just minus. And that's how you do partial fractions.